Welcome to Delineating Sub-Watersheds in ArcMap with Dan Jones and Matt George. When trying to create sub-watersheds inside a broader basin, geoprocessing tools can be run one by one in Esri's ArcMap program to achieve the desired result. The problem is this quickly becomes a rather lengthy process, particularly when multiple basins are to be analyzed, possibly multiple times. We, Matt George and Dan Jones, have solved this problem by creating a Python script that creates an atlas of sub-watersheds of hydrologic unit codes, otherwise known as HUCs, with very minimal user effort. We now proceed to explain how to find the necessary data, how to find, download, and use this script, and how the code produces the sub-basin atlas. To perform this analysis, we will need several datasets. One of these is a digital elevation model. There are many places you can download DEMs, but the place we chose was earthexplorer.usgs. When you click on the link, it will take you here. Then all you have to do is zoom to the area of interest, make a wide bounding box around the area you will analyze, and after having done this, click Datasets. Then click Digital Elevation. You can use any of these to obtain DEM data, but the one we have chosen is GMTED 2010. Then click Results. After a moment, it will generate your results. Click this button with the green arrow, and then select what size DEM you want. For our analysis, we use 7.5 arcsecond. The next piece of data we will need is a watershed HUC shapefile. The best place to obtain this is from datagateway.nrcs.usda.gov. First, you'll need to select the state you're interested in. For our analysis, we have chosen Utah. Then it will take you to the WHAT page, and since we are doing analysis on HUCs, scroll down until you get to hydrologic units. We have chosen to download the 8-digit watershed boundary dataset. The only difference between these and other digit watershed boundary datasets is the size of your HUC. As you choose a smaller number, it will make your HUCs larger and therefore fewer. Click Continue. The format you want is an Esri shapefile, as we will be using ArcMap. Choose the appropriate projection. For us, that's UTM Zone 12, NAD 83. Use the default delivery method, FTP. Then click Continue. It will ask you for some contact information. Fill this out, and it will email you the dataset as soon as it is ready. This will only take a few minutes.
After getting your HUC shapefile and DEM, you will need to obtain the Python script and ArcMap document necessary for running the analysis. To download these, go to this website. A link to the site is also included in the description of this video. On the website, click here to download the data. Once in the Google Drive folder, simply click on Add to Drive in the top right, and then open this in your Google Drive. After adding this folder to your Google Drive, you can download its contents by selecting the folder's name and then choosing Download. To save time, we will cancel this download and show you a copy that was downloaded previously. You will need to unzip the folder, and inside you will notice that the MXD file shows up as a Word document. Some sort of error with Google Drive. To work around this, you can delete that file and then opt to only download the MXD file from the Google Drive folder. Then you can simply add this file back into the downloaded folder. You will have a few customization options for this project. You can change the shapefile properties such as the stream width and color, or the watershed polygon color and transparency. You can also change the outline that displays on the secondary data frame. We chose Utah as our boundary shapefile, as that was the area of our analysis. You can change the data source by going into Properties and selecting Set Data Source. You will also want to update this text box with your name and the projection you use. To run the script, click on Catalog and navigate to the toolbox inside that Watershed Atlas folder. You will see the script called Create Watershed Atlas. Double-click on this script and this box will pop up. You can then select your Huck shape file, wherever it's saved. Ours is saved in the sample data folder. You will also want to select the DEM for your area. The threshold parameter defines the beginning of your rivers depending on how much area upstream flows to that point. To create many smaller subbasins, choose a relatively low value. For our dataset, 6,000 seem to produce an aesthetically pleasing amount of sub-watersheds. You may need to play around with this parameter to find the best option for you. Then, choose your coordinate system. And for this final parameter, be sure to navigate to the location of the main Watershed Atlas folder. When you click OK, the script will begin to run. In this window, you will notice that the program tells you which Huck it is currently working on, as highlighted. The ArcMap display will update for each Huck, including the name of the document and the page number. We will allow the script to run for 2 full Hucks before canceling it to show you the output file. The output PDFs appear in the Watersheds folder of the main Watershed Atlas directory. In this folder, you will see a PDF for each Huck, as well as a composite atlas. Here's the atlas we made from the first 2 Hucks. As you can see, we have the Hamlin-Snake Valleys watershed and the Lower Virgin watershed. Here's a sample result if we had allowed the code to run to its end. As you can see, the PDF has 63 pages and contains all of the Hucks within our shapefile.
Okay, so for all you tech gurus, let's take a look at the Python code that creates this Atlas PDF. To begin, we import any necessary modules and check out any necessary licenses if they are not already checked out. Next, you will notice we call getParameterAsText several times. This is calling user inputs from the Create Watershed Atlas script. As you can see, the Huck shapefile, the DEM, the threshold, the coordinate system, and the location of the Watershed Atlas folder are all called with this getParameterAsText function. The overwrite output is set to true to overwrite any intermediate files. We set our workspace and our Scratch workspace. Here in lines 20 through 23, we define our folders and a path for our PDF. Then in this if statement, we check to see if the PDF already exists, and if it does, we remove it so a new one can be saved. We also define the path for PDF doc. Here we create several geoprocessing variables, some of which are called from the user inputs with this getParameterAsText. Next, we create map document variables. MXD standing for the current project, WDF standing for Watershed Data Frame, that is the main data frame in our project, and LYR standing for the layer, Watershed Polygon. Next, we define loop variables. Rows is a variable that remembers which row we are in the Huck attribute table. I is a variable that updates page numbers. Let's take a look at the two functions we use in this script. The first is called threshold try. Before I describe how threshold try works, let me describe why we need it. If the user were to input a value for threshold that is larger than the number of cells in a given HUC, ArcMap would throw an error and break. To avoid this problem, we have written threshold try so that the script automatically decreases the threshold by 50% each iteration until it works. This is illustrated in this try except loop. The second function we define is called geoprocessing. This is appropriate as it runs all our geoprocessing tools. To begin, we define a variable called SQL, which looks at the name property of the row variable and helps us use our first tool, select. It selects the watershed loop from the HUC shapefile. Next, we extract by mask the DEM from that HUC of interest and we fill it. This just smooths any imperfections. Next, we compute the flow direction and flow accumulation based on the DEM, on the filled DEM. Then we use raster calculator to change all the cells that are greater than our threshold to 1 and all the cells that are less than or equal to our threshold to empty. Then we run threshold try to make sure that our threshold does not crash ArcMap. Then, after a suitable threshold has been found, it continues, jumping out of this except clause into feature vertices to points, then to snap pour points, then to watershed. The last geoprocessing tool we use is called raster to polygon. This turns the watershed raster into a polygon.
Now we'll take a look at the main loop of our code. It starts off by looking at the first row in the attribute table for the HUC shapefile and performs the geoprocessing tools on that HUC. The map document name and page number is then updated in this loop. It checks for the text element that contains name and replaces that with the name of the watershed plus this string watershed. It does the same with the page number, but with I as the counter. Our code then zooms to that watershed polygon, so the display is correct. The following function allows ArcMap some time to process and catch up, and refreshes the active view. The next step is to export the map and append that page to the composite atlas. Our code then saves that PDF and closes it and reopens it. Lastly, we reset those text elements so that the next time through the loop, it will update them accordingly. We also reset the threshold variable in case it went through the threshold try loop, as well as increasing the I counter. After it has run through this loop for every single HUC in the shapefile, the code saves the document and closes it. This is the end of our code. Alright, well, this concludes our video presentation. We hope that you'll find this useful in delineating sub-watersheds using ArcMap or in your own Python coding. Thanks for watching.